Yes, my name is Sébastien, and my background is in speech and language engineering back in Cambridge, and I was actually fortunate enough to have Tony Robinson as one of my lecturers in speech analysis at the time. I've been working in the speech industry for like 10 years, I guess, and I've now got my own two hats. I'm working on statistical machine learning in PhD research, and I'm doing this consultancy job with dawin, which is a German SME. We produce, we were actually a speech recognition systems integrator, I'd say. And this is our mission statement. We make speech systems that are used in plants or in lab environments or out in the field. They're usually closed vocabulary, so the kind of things that is not very fashionable these days, where all you got to speak about is large vocabulary, continuous speech recognition. We make closed vocabulary, small vocabulary systems with very short latency, embedded because usually they're in settings where we have no wireless connectivity, and very robust to noise, and that means small vocabulary because our users will use them maybe all day long, and they just can't care less about conversational speech. So it's kind of like the opposite of all what the hype is about, where you want to have a conversational interface, you want to have very large vocabulary and support sort of intelligent dialogue if you can. My argument today is going to be about the advances, like the specific advances in pointing into the mechanics of speech recognition engines to make you understand where deep learning made an impact exactly in speech recognition systems. So one very important point to get is that there's been this paradigm shift positively in the last 5 to 10 years, where we went from a situation where we had Gaussian mixture models. I'm going to refer to these as GMM as everyone else. I'm going to use the acronyms throughout. We were using Gaussian mixture models, acoustic models, with a hidden Markov model backbone. I'm going to come back to what a hidden Markov model is in a second. And language models, which were n-grams. And we've moved to the current state of the art, which is we have acoustic models which are feed-forward deep neural networks with several hidden layers, as opposed to a single hidden layer, which is what people tried in the 80s and 90s and didn't work so well, and where language models are recursive neural networks. I'll also briefly mention other recent developments which then might or might not turn into the future state of the art, provided they overcome a number of hurdles. And a number of them are refinements of the innovations in acoustic and language modeling. So, for instance, using convolutional neural networks in acoustic modeling, using more clever forms of recursive neural networks such as LSTMs or different sources of information, but still keeping the current established hidden Markov model backbone of things. And then there are approaches which we call end-to-end approaches, which aim to replace the backbone that's been in use in speech for the last 30 years, like ever since the 80s and maybe before actually, altogether. And so this is a much more radical thing. So deep down, an ASR system is quite a different beast than what we've been speaking about in the rest of the sessions today, i.e. mainly vision or video understanding systems. An ASR system is still very much a probabilistic system and rests on foundations or on concepts such as the noisy channel concept that were sort of established in the 80s. So it's much more of a complex architecture with different components, different probabilistic components than, say, an image classifier, where pretty much your CNN, however complex it may be, is your actual system. Right? In a speech system, you've got several components working together, and as I think Tony pointed out just before, improving performance in one component is not necessarily going to give you an overall improvement in the end metric you're interested in. So they are probabilistic models. The input is audio. The output is usually something that gives you a probabilistic match between the audio and the word sequence or hypothesized word sequence you're interested in. As the output, just like in image classification, you will get maybe a ranking of solutions. The fact that it's a probabilistic model with its parameters inside means that you've got the steps still of training, where you want to learn the parameters, and then of cross-validation or tuning, where you tune hyperparameters just as you do in, say, deep learning when you when you learn the number of hidden layers you should be having, or the number of nodes per hidden layer. And then you've got the sort of inference step. Inference is the word we use in machine learning, and in ASR, in the speech community, we'd use the word decoding to speak about the actual fact of recognition, which is a compute-intensive step that entails considering the multiple candidate word sequences and sort of scanning through them and picking the one with highest posterior probability. So there's quite a natural split in an ASR system between the acoustic part and the language part, of the acoustic model and the language model. The acoustic model is the one that connects sounds with phonemes if you have a phonetic representation. What I'm saying on this slide and on the next few slides doesn't apply to end-to-end systems, where you can happily do away with phonetic representations altogether. But still, when you have an acoustic model, this is what it's like. And if you write it down in terms of probabilities, what you're looking at is a likelihood. It's a probability that, or a sort of probabilistic match, if you want, of the audio output, assuming that you've got a word sequence to start from, or a phonetic sequence. I'll do as if these two were the same exactly. And then the language model is a prior in sort of Bayesian terms, and it tells you about the likelihood, the probability of the next word given a history of words. And then putting both together, you're in position to do recognition. If you've given an audio signal, putting the two together, you can do recognition then. Now, to make you understand why and how we use hidden Markov models in speech recognition, I'm going to take you through a few steps, which I hope are not going to put off anyone, but I think they make sense. The overall picture of the speech recognition system is this. We have a feature extraction step where we do some pre-processing. We have the search or decoding sort of apparatus or routine that is running and doing the actual job of finding the most likely word sequence given the audio that you've been said. And this thing is fed with the acoustic model, the language model, and the pronunciation model, and a lexicon in general. What you need to know is that, and it's not obvious if you come from outside the field, is that the very first step and assumption in speech recognition is that we'll be splitting up the incoming audio into into frames or bits of audio of equal length, usually about 10 milliseconds. Maybe they overlap, maybe they're sort of from a Hamming window or something. But this is roughly the picture, the segments of audio of equal length. And the model, the probabilistic model we're going to feed these sequences or these frames of audio into is the hidden Markov model. You can think of this as a finite state machine that each time you move a step in that finite state machine, you'll be feeding it with an audio frame. In this picture at the bottom right here, you have transitions from states to state, and you have reentrant transitions that take you from one state to the very same state. But in going that step, you've been absorbing or using one frame of audio. And then you've got the bit at the top left here, which is an emission model. So these are the two bits in the acoustic model, really. An emission model that will take as the input an audio frame and produce a probability that the audio frame was generated from a given phoneme. The sort of epsilon here stands for a phoneme. It doesn't stand for the thing that in automata theory you label as the empty transition. So here I have an HMM that corresponds to a vocabulary of yes and no, as you might have guessed. So I've labeled the states with the corresponding phonemes. This is about the entire truth, except that in general people use triphones and they don't use HMM states that are just exactly one phoneme. They're subphonetic states. A typical DNN that is used as the emission model, and that's the main innovation, the bit that brings most impact in terms of performance. A typical DNN used as the emission model is something that looks like this. It's got 5 hidden layers, 2048 nodes, or maybe a multiple of that, but not much more, and these characteristics. The big improvement that happened in 2010, 2012, is that people for the emission model, so the bit at the top left, they were used to use Gaussian mixture models here, and they've replaced them by deep neural networks. And that alone brought improvements of about 30%. This is a table from a 2012 article that was kind of historic because it was co-authored by 4 research groups from the University of Toronto, from IBM, MSR, and Google. And the results that they displayed were word error rate improvements of about 20 to 30%, according to the test set they were working on, and etc. And these are the things that people still see in a very consistent way. So replacing the HMM emission model from Gaussian mixture models to deep neural nets, this alone brought this enormous improvement. The second part that brought a very big improvement and changed the state of the art is in language modeling, where we're going from the n-gram language model, which usually takes the form of the language model usually takes this prediction function shape where you're predicting the probability of the next word given a history of words. So in n-grams, you do this cleverly by sort of cutting off the history at a reasonable point so that you're avoiding data sparsity but still have a history long enough to make a meaningful prediction about the next word. And the new state of the art are recursive neural net language models. So they're pretty simple to understand. The output layer is a softmax layer because you want to make a prediction over the entire vocabulary. So this is a very large, a very long layer actually. It's got the size of your vocabulary, so it might be 100,000 nodes in the last layer. The middle layer here is a hidden layer that's much smaller. It's maybe a few hundred nodes large, and this is the typical word embedding, word vector embedding that you get from word to vector or what be it. And the layer before here, the WT-1 thing, this is just a one-hot vector. You make this recursive by feeding in a history of words and their word embedding representations from layer to layer, and you have a new language model here. And this in turn brings you around 10 to 20% relative word error rate improvement. So this is the other very big improvement that was made in the last, indeed, 5 to 10 years. I'm running out of time, apparently, so I'm going to skip a few slides and take you to the end-to-end systems, which I think are a very radical new thing that might redefine the state of the art in, say, maybe 3-4 years. The idea is forget about the HMMs, have very large neural nets with the appropriate structure, and do a sequence-to-sequence classification. So start from the audio sequence and predict a character sequence, maybe. So ideas in this direction are the bidirectional recursive neural nets or bidirectional LSTMs. In fact, Alex, who spoke this morning, was one of the first to try this out much earlier than 2014, but his paper from ICML last year was a nice display of what could be achieved here. So you have different approaches, obviously, and people try different things. And at each, so in these 3 papers I mentioned typically, they do away with more and more of the existing sort of baggage. So in the first paper, you still had an underlying HMM-based system that you would, the output of which you would rescore using a bidirectional LSTM. Okay, so yeah, getting somewhere, but not there still. In the Hanun paper, the Baidu Deep Speech paper, you still needed an n-gram model, a word n-gram model, to rescore the output of the bidirectional RNN they were using. So still, you absolutely needed a lexicon, you needed a language model, and that's what it rested on. It got good results with. And then in that last paper by Andrew Maas et al., you do away with lexicons altogether because you do character level prediction and you have a character level RNN language model. So as we go, we do away with some of the heavy baggage we've been using our HMMs with, and hopefully simplify the architecture enough so that the pipeline, which currently still is quite complex, for a speech recognition system, is vastly simplified. And obviously, that's one of the promises. However, there are hurdles to achieve this because we have very fine-tuned real-time decoders that run on small systems, on your smartphone, and we need to beat these. So end-to-end systems are very interesting, but they're certainly not there yet. They're not defining the industrial state of the art because they're just way too slow in terms of real-time decoding. So I'm out of time, but I'm gonna say a word, give another word of caution, just like the panelists did a second ago, against the hype for deep learning and sort of ground the discussion in reasonable machine learning and speech community state of mind reflections. So people in the speech community are very much aware that, yes, there is this trend. Deep learning is solving a whole lot of problems and bringing, in terms of word error rate, bringing a lot of performance improvements. However, there are some critics also because some papers are a bit partial when they sort of for different reasons, when they advertise achievements of deep learning methods or deep learning successes. So some people are a bit biased against what they see in papers because they say that's not a fair comparison to existing state of the art. And then there's a very important point to be made, which is that the speech community by itself, so I was at Interspeech in Germany, which is a major speech conference 2 weeks ago, early September. And there the state of mind was very much like, okay, yeah, there's deep learning, but the bulk of the sessions or the bulk of the issues that people were speaking about are the kind of speech recognition invariant issues that are technique independent or model independent, which is robustness and adaptation. So what you do when your test data doesn't, like your recognition data, test data doesn't match your training data, right? You have an adaptation problem here. You want to do some transfer. What if you need to do speaker adaptation? These are sort of problems that run along the history of speech recognition ever since it exists, and that's not going to stop with using deep learning in any way. Then there's seeing speech as a signal and exploiting much more than what we currently do, which is just exploiting a tiny bit of the information that's contained in there, but doing away with all the prosody bits, for instance, so doing away with important information for saliency, for instance, speaking rate or volume, like amplitude, pauses, and intonation. These are things that are largely ignored currently by speech recognition systems, and then all the dialogue phenomena, obviously. The understanding bit is another one, and there's all the rest with engineering, latency, footprints. These are permanent problems, and what I mean to say here is these are not gone by just using deep learning. So deep learning is certainly just a phase or just one step in the sort of incremental development of things. Here are my own unwarranted predictions made hard by the fact that it's about the future. I don't think we've squeezed out all the performance, certainly in speech, that we can get from deep learning models. I think there's still a lot to be done. And I am also deeply convinced that the successes of deep learning today stem from a happy conjunction of several facts. One is the conjunction of the model capacity of deep learning models. These are models with easily 10 to 100 times more trainable parameters than GMM models from 5 years ago. So 10 to 100 times more parameters means a hell of a lot more capacity in machine learning terms, and a hell of a lot more ease to fit the data, and hence problems with overfitting, which no one was seeing when we were using Gaussian mixture models. So the conjunction of having this sort of high capacity models with having the right regime in terms of data, so that means we've got the right size of data sets to work with these deep learning models, and at the same time we have the right specialized computing infrastructure, i.e. GPUs and parallel CPUs to work with them. So we've got this conjunction of facts that makes it so that it all works out very well. And I think this is by no means unique, and I think that as specialized hardware will influence the next generation of models, so will the continued increase in the size of data sets probably be sort of by natural selection of computational models. They will favor a different type of models than deep learning models, most probably. Thank you.